Let's start today's class. So, in the previous class, I think it's okay. In the previous class, we learned about how to represent floating point numbers, and then actually the floating point numbers are different with the integer type numbers. But it's because the integer type number system is simple, relatively simple. But the floating point numbers, so it's like the normalized floating point number in the decimal numbers. It's a little bit complex, which means that so we need to represent the sine bit and then fraction part and exponent part. And then this number representation is different from the integer type number systems. So, but you know, this is actually the standard. So the standard is specified by many researchers in the research community. So we can just follow the standard to represent this floating point number system. And then also I explained that the floating point units, which means that the arithmetic units for floating point numbers are also very complex. So compared to the integer type arithmetic units. So it is because actually it's the same to our decimal number system. So if we just calculate the real numbers like floating point numbers, so it's a little bit difficult, a little bit, just a little bit, so a little bit tricky. So and it's the same to the computer hardware. Okay, and then then now we are in the chapter 4 of the textbook. So in chapter 4, we will learn about the hardware architecture of the CPU. So actually in chapter 2, we learned about the instruction set architecture. So actually in chapter 2, we learned how to design instructions. And then actually the instructions are given to the computer processors. The computer processors generate result defined in instruction set architecture manual. And then, so that's what we learned in chapter 2. So we learned about this instruction set architecture. And then also we learned the result by each instruction. Okay. So in chapter 4, that's what we learned in chapter 2, the chapter 2. And then in chapter 4, we will learn about the detailed hardware architecture, which means that we will learn about the inside of a processor, the hardware architecture of a processor. So actually, to the software engineer or actually to the software, hardware is just a black box. So what does that mean? So actually, so we learned about the abstraction and then the layers in the computer systems. So in chapter 1, actually the introduction part of this course, we learned that the computer systems are composed of many layers, and then actually the upper layers receive some signals or things that output from the lower layer. And then actually, if we focus on a certain layer, we don't need to understand the detail of the lower layer. It is because so we can just understand some interface signals. And then it's the same to the software. So to the software, the instructions are just an interface between hardware. So actually to the software engineer or software applications hardware, so that means that the processor is just a black box. Okay, so which means that to the software engineers, it's okay. Actually, the instruction set architecture just define this result, the architectural state. So it means if the correct results are generated, and that's okay. It's just a black box. But in this course, we will learn about the hardware architecture, which means that the detailed structure of this processor. So to us, it's not a black box. So we will learn about the detailed hardware architecture of this processor, and then which means that actually when we design a processor performance. So actually, I also explained in chapter 1, performance and cost are very significant factors. So which means that we need one very fast processor. So which means that the performance should be high. Also, cost should be lower. So, but in this course, we just focus on the performance of the processor. Okay. So actually, the hardware engineers focus on the performance and cost of the processor. So which means that hardware engineers try to build good processors, which means that for fast processor, and then also the low cost processors. Okay. So we are going into this processor, inside of the processor world. Okay. So in chapter 1, we learned about the performance factors. So which means that we define the performance of the processor in chapter 1. Also, we learn how to measure, which means that how to compare the performance of two different systems. So we learned that, so it's a very important equation. Execution time, what is execution time? It's instruction count, CPI, multiplied by clock period. So as we mentioned in the chapter 1, the instruction count. So these are number of instructions given to a processor. So actually our high-level language code is translated into the machine code, and the machine code includes many instructions. So actually the number of instructions are determined by this Python, instruction set architecture and compiler. So in chapter 2, we also learned how compiler influences the instruction count and performance. So we can set a performance compiler optimization factors, actually the compiler optimization levels. So we can adjust some optimization effort by compilers. So by adjusting these compiler optimization levels, we can also increase or we can decrease the performance of our compiled software. And then how about the CPI and clock period? So usually the clock period is the clock period is determined by hardware. So which means that the clock period is the clock period. So we frequently mention the clock frequency of the system, but actually the clock period is the inverse of the clock frequency. So clock period is determined by hardware. So which means that the clock period is determined by the semiconductor technology and also the design method. So actually also we can build very simple design, so which means that this simple design can work with the very fast clock. But if we just build a very complex design, then we may need to use the very slow clock. Okay, so T is determined by hardware. And then CPI, how about the CPI? So we also learned that the CPI can be changed by compiler. So which means that we can actually the CPI can be influenced by compiler optimization level. Also, the CPI is influenced by hardware architecture. Okay. So if we see that this performance equation, so this part is just a software part, Usually, I said usually, and then this part is the hardware part. So hardware and software are both important for the performance of our computer system. So in chapter 4, we will learn about the hardware architecture, and then so now we are learning about the RISC-V instructions and architecture. So in chapter 4, we will learn how to build computer processor that can execute RISC-V instructions. Okay, but we will not learn about the detailed hardware architecture. So in chapter 2, so we just learn explore the very basic so baseline instruction set architecture of RISC-V. But our hardware cannot. So actually, we learn about the very simple hardware architecture. But if we learn about if we just consider the hardware that support all kinds of RISC-V integer instruction set, then it will be complex, which means that we need more time, we need more lectures for learning the entire RISC-V integer type instructions. So actually in chapter 4, we will learn about the very simple design, the simplified processor that can support only a few instructions, only few RISC-V integer type instructions. So we assume that our processor will support these instructions. So memory instructions. So our processor will support load and store instruction. So actually, LD means the load double word and SD means the store double word. And then we assume that our processor will support these 4 arithmetic and logical instructions, add, sub, and or. And then 1 branch instruction, so BQ. So we assume that our simplified processor will support these 7 instructions, right? The 7 instructions. Okay. Okay. Then I will skip this slide because I will explain about some basic logic design conventions. So in chapter 4, we will learn about the hardware. So which means that we will learn how to build hardware. So you need to know the basic convention or basic knowledge about building very simple system design. Okay, so before going into some process architecture world, so I will briefly explain about the very simple logic design conventions. So what is the hardware? So I repeatedly mentioned that the CPU is the system. So which means that the system just receives the digital data, then digital data is composed of just 0 and 1. So which means that digital data is composed of many bits, and then each bit has only 2 values, 0 and 1. And then as I explained, 0 means usually 0 means low voltage, so which is just the ground. And then we can say that the ground is just a 0 volt. And then we can represent the 1 as the high voltage, like a VDD, it's a supply voltage. And then we usually in the CPU, we use the 1 volt, around the 1 volt for the supply voltage level. So if the voltage level is 0, then it represents the number 0, like ground. If voltage level is same to the ground level, so which means that the data is 0. And then if the voltage level of the certain data is 1, so 1 volt is the same to the supply voltage, then we can say that this value is just 1. Okay. And then I also mentioned that each bit each bit represents the 0 and 1. And then actually the digital data is composed of many bit data. So it's also true for these computer instructions. Also, we learned that the RISC-V instructions have 32 bits. Okay, so this is just the digital data. So which means that RISC-V or a single RISC-V instruction includes 32 bits that we can represent actually two different data in this 32 bit data. Okay, and then using this digital data, the computer hardware, which is the system hardware, need to generate the processed result. So the processed result of the system is also digital data. Okay, so we need to know how to generate a certain result from the basic logic gate. Okay, so first we need to know about some basic logic gate of the system. So what is the logic gate? So I mentioned that the data is composed actually each bit. The single bit of the data has only 0 and 1. And then we need to represent we need to generate the result based from this bit data at the 0, 1. And then so actually the result of the system is generated by basic logic gate like AND, or not, and exclusive OR. So what is the AND gate? So this slide shows the very simple, very basic combinational logic. The first combinational logic is the AND gate. So what is the AND gate? So AND gate has the two input ports, A and B, and then based on this input data A and B. So this is the bit data. Okay, so we can represent the combination of A and B, like 0, 0, 0, 1, 1, 0, 1, 1, because there are 24 cases. Then what is the result? The results are 0, 0, 0, 1. So it's the logic gate. So and the definition of the AND gate means that if the two bit data are both ones, then the result is 1. Otherwise, result is 0. Now, how about adder? We can build the adder logic with the full adder gate, full adder logic actually. So we can build the adder like this. So A is into the input of the adder gate, and then the adder logic that gate. So it's a logic, and then B is given to another input of the adder logic, and then the output is generated. And then can also build the multiplexer with the selection signal, and then also we can build the arithmetic logic unit called the ALU. Okay. So the ALU, receive the two input data A and B, and then the function of this ALU is determined by some selection control signal, the ALU selection control signal. And then based on this defined function, the ALU generates the result, so defined result. Okay. So our processor will include the ALU because in chapter 2 we learned about the various arithmetic and logical instructions of RISC-V. So we learned that the RISC-V supports add, sub, also RISC-V supports the logical instructions such as exclusive OR and OR. Okay, and so the RISC-V supports the various kinds of arithmetic and logical operations. So we can select some operations required for different instructions, and then based on this selection signal, then ALU generate the predefined output based on the two inputs. So these are called combinational logics. So what is the combinational logic? So in this slide, the combination element is defined like this. Operator on data and the output is a function of input. What does that mean? The combination element looks like also a black box. So it's a combinational logic. I frequently use the CL because it's combinational logic. So combinational logic receive multiple inputs, also one input. The multiple inputs usually, so receive the multiple inputs, and then based on these multiple inputs, combinational logic generate the defined output. And let's see, so which means that it's very similar to the y equal f(x). So this value of y is determined by input variable x, input argument x, and then based on the defined function. And it's the same to the combinational logic. Input is given to the combinational logic, and output is generated. And then this output is just determined by input signals. That's it. It's very simple. So why do we need to learn about the combinational logic? But so we need actually in a real world we need to consider the delay. So that means the time. So out is generated from the combinational logic, but after some delay, delta t. So this is the real device, so real CMOS logic. And then actually the CMOS logic have delays because the CMOS logic has the resistance part and also the capacitance part, and then resistance and capacitance determine the delay of this CMOS logic. And then we can build the digital system with the CMOS logic. So actually our digital system has the delay. So combinational logic means that so in output results are determined by input, but after some delay. So we can just understand the combinational logic like this. And then these are the examples of combinational logic. Okay, so just as you can see, that if we see the AND gate, the what output of AND gate Y is determined by input values. So that's why AND gate is the combinational logic. How about the adder? Output of adder is determined by two inputs A and B. And that's it. So those are combinational logics. And then let's see how to build. So we will learn about actually. So you are required to simulate the very simple gate with the system value. So I'm showing some examples of Hdl code for combinational logic. So this is the system value module. Okay. So each module starts from the module. Okay. So we can build module with the module statement. So I said we can understand the combinational logic like a black box. Okay. And then so write the Hdl code, it means the hardware description language code, means that we build a code for this inside of the module. Okay. And then so these modules have input ports and output ports. So this module received input signals via input port and then generate the output result via output port. That's how digital system modules are built. Okay. So let's see the end. So this is the module name. So we can start from the module. So this is the syntax of the system variable. And then we can start, this is the module name. So we are building AND gate. Actually, I cannot use this name, but this is just the example. So, and then this module means that AND gate has 3 ports, and then the port names of the 3 ports are A, B, and Y. And then also the input ports and output ports are defined here. So we can say that A and B are input ports, and then Y is the output port. And then we define the output. So this is the AND gate. So you can see the very great level here. So we can define output as the Y equal A and B. So these are input of the AND gate, and this is the operator of the system variable that represents the AND gate. And then this is the output. So we can simply build the AND gate like this. So this is explained in the lab document. Now how about the adder? So it's the same. So this is, we start from the module. So and then the module is ended with the AND module syntax. So we can start from the module, and then this is the module name. Then as you can see, oh, this module has 3 input and output ports. Okay. And then you can see the width of the ports. In this module, in A and B are declared as input signals, and as you can see, the width of each input is the 8 bit. So, and then bin number from 7 down to 0. So we can declare the input signals A and B, and then each port has the 8 bits from 7 to 0. And then output is 1. And how can we define the output? So this is the skeleton, so black box. So we define the A, B, and Y. And then this is the 7 down to 0. These are 7 down to 0, and then this is 7 down to 0. That's adder. So we declare the module like this. And then inside of this module, we define the behavior model. So that means the operation of this module. And then simple. So we can simply implement adder with the Y equal A plus B. In the system variable, we can use the operator plus or add operator. Okay, and that's it. So if we build a system variable module like this, then our simulator will generate some behavioral model of our digital system module. Okay. How about the multiplexer? Okay. So if you see the multiplexer requires 3 inputs, like these inputs and selection signals, and then 1 output. Okay. I0, I1, and Y are defined. And then I also that the width of each input is 5 bit. Okay. So we define the input port like this. I0 and I1 as the 5-bit input port, and then S is the selection signal. Okay. Now Y is the output. Then how can you define the behavioral model of this multiplexer? As you can see, Y equals the multiplexer, the output is selected by selection signal from 2 or multiple inputs. So Then equal S equal 1 to 1. So that means that S is 1, then output becomes the I1. Otherwise, output is connected to the I0. So if you see the syntax of this multiplexer, it's very similar to the C. Okay. So I saw some examples of system value code for combinational elements. Okay. And then first, our digital system works with clock signal. So what does that mean? When we run the performance, then the performance of the CPU is determined by clock period. So it means the clock frequency. And then what's the clock? So clock is the repeated up and down signal. And then clock period means that just the time between the rising edge of the clock and then the next rising edge of the clock. Okay, this is the clock period. So why clock signal is important in the system design? So if we just build the combinational logic, then actually the delay of this combinational logic is influenced by state of input signals. Okay, so what does that mean? If the input signal has the 1001, 1001, and then 1000, and then the result is generated at some delay, like 1 nanosecond. But if the input signals are changed, like 0000, and then 0001, then the delay can be different, like 0.5 nanosecond. So actually, the delay of this combination logic can be changed by the state of the input signals. Okay, so which means that this delta T is various. So and then we cannot build some stable system with these variable delays. Okay, so think like this. There are many workers here, and then the delay of the workers are so different. Then we need to give some same. So actually, this is the input, and then the input need to go through the multiple workers like here, but some delay of these workers are different by some stage of this signal, so some different by some time and some other some environment. So how can we make the stable system? Stable system is that we can give the same time for the different workers. So which means that if this worker completes his job, and then after some period of time, then this output of this worker is delivered to the other workers. Okay, the next worker, and then during the same time, this worker completes his job, his or her job, and then the result of this worker is delivered to the next worker. But this time period is the same for each worker. So if we design a system like this, then we can build stable system. And then it's the same for the digital system design. Actually, the digital system design works with the clock signal. And then the clock signal has the repeated signal. And then the clock of this period, clock period is fixed. So fixed value. So we can change the clock period, but usually the clock period is fixed. Okay. Then how can we make the very stable design? Okay. So I explained that this is the combinational logic. Then combinational logic is the input and output, then generate the output. But this delta T of the combinational logic can be changed by input signals. So then how can you make the very stable signal, a stable system? So the input of this combination logic can be controlled by clock signal. So which means that this, actually this is the D flip-flop. So this is the D called the D flip-flop. So this is, and then D flip-flop works with the clock signal. At the rising edge of the clock, this D flip-flop gives the input signals to the combinational logic. So at this time, the input is given to this combinational logic. And then after some time, some delay in the T, this combinational logic will generate the output around here or here. So it can be different, but output is generated at this point or this point. It can be changed by input signals. Then, after the output of the combinational logic, there is another D flip-flop. And then D flip-flop is synchronized by also the clock signal. So, even though the result is generated earlier than the rising edge of this D flip-flop, this result is sampled by at this point by this D flip-flop. So, which means that the output can be generated here and here and here. But even though the output can be generated with the various delays, the output is sampled by at the same time by the clock signal. So this output can be delivered to the next combination with this clock. Actually, this is the basic design of the pipeline. So with this D flip-flop, then we just make the combination logic. The output of the combination logic is sampled at the same time. Okay. So then you can make the safe and stable system with this complete D flip-flop. And then, so this type of logic is called the sequential logic. Okay, so sequential logic means that the state is also stored, and then the output of this sequential logic is determined by stored state and the input. Okay, so if we just make the sequential logic, then we can also make some logic that can store state. So it's similar to the memory. Okay, so just the states are stored. Then usually, our digital system has the forms like this. So there is the state and so like this. So actually there is a state element before the input of the combinational logic, and then this state element is sampled by clock signal, the rising edge or falling edge. And then there is combination logic between these two state elements, and then the output of the combinational logic is sampled by another state element. That's the basic digital logic design. Okay. So then how can we determine this clock period? this clock period. So as I mentioned that the output of this combinational logic should be stabilized earlier than the rising edge of the next clock. Okay, so this is the clock period. So it's the rising edge of the next clock. So output of this combinational logic should be stabilized. So which means it's determined, so stabilized before it's rising edge of the clock. Okay, so somewhere here. So which means that this delay of the combinational logic is size the clock period. Is T, a clock period. Okay? So if the delta T is high, then we need to make the clock period longer. So which means that the clock frequency is as lower value. Okay, the clock frequency. So this system has the low clock frequency. And then if the delta T is small, which means that we can make the faster clock, so clock frequency is high, then the system performance may be better than the system that has the lower clock frequency. Okay? So actually we use the D flip-flop as the state element here and the state element here. And then D flip-flop looks like this here. So this is the D flip-flop. And if you see this D flip-flop has the input port and then output port and then clock port. So the definition of the D flip-flop is that at the rising edge of the clock, the input is sampled and then sampled here, and then the value at the rising edge of the clock becomes the output. This Q becomes Q. What does that mean? So in this example, the D is changing. So value of the D is changing at this point. But you know, the rising edge of the clock is here and here. So change of input is reflected at this point, at the next rising edge of the clock. So Q, this is the output of the D flip-flop is same to become same to the is sample the input at the some delay from the rising edge of the clock. Okay? So we need to remember that in the D flip-flop, the input is only sampled at the rising edge of the clock here. So which means that even though the input is changed here, this changed input is reflected at the rising edge of the clock. Okay, this is the operation of D flip-flop. And then this is some example code of the D flip-flop with the system variable. You know, this is the module name, and then as you can see here, it's a D flip-flop. D flip-flop has 2 input ports and then 1 output port. So this is the clock ports. So it's a clock port, and then this is the input, and then this is output port. And then what is the behavior model of the D flip-flop? So in order to implement the D flip-flop with the system variable, we need to use the arrays underbar F statement. So this is the some different. Well, so actually in the system variable, in order to implement the D flip-flop, we need to use the arrays underbar FF. So and then this is the sensitivity list of the arrays statement. So sensitivity list means that this arrays statement is executed if this condition is true. Okay. So what's the condition? The condition is the positive edge of clock. So which means that at the positive edge of the clock, this is executed. So this is reflected. Okay. So output Q is the E. So this is the behavioral model of the D flip-flop. I believe you can understand that this is sensitivity list, and then so if this condition is true, this part is executed. So as the behavior, the executed behavior is Q equal E. So D flip-flop. And then this is the example code of D flip-flop with the negative reset. So what is the reset? So the reset means that if the reset signal is associated to the D flip-flop, then output becomes the 0 regardless of the input values. So which means that the reset signal just reset the output port of the D flip-flop. Okay.
The other slide, can you say what that word means again?
This one?
Like, yeah, the one that you wrote, what does it mean? Like, can you say the word?
Which one?
The one that you wrote down.
This one?
In the right thing.
It's a sensitivity list. It's sensitivity list. So sensitivity list means that. So this is the always statement, okay? And then this always statement is reflected if the condition of the sensitivity list is met. Okay, so which means that in this example, the condition of the sensitivity list is the positive edge of clock, it's the pass edge clock. Okay, so which means that this always FF is reflected if the positive edge of clock is met. Okay, actually at the positive edge of the clock. Okay.
Thank you.
Okay. So let's see this example code. So this D flip-flop has the 4 ports, like a clock port, and then reset port, and then input and output port. So this is the input port, the clock and reset signal is the 1-bit port, and then input E is the 8-bit port, and then Q is the also 8-bit port. So this is output. So the behavioral model of this flip-flop with negative reset is somewhat different. So negative reset means that if RST underbar B, this is the negative reset. If the negative reset is 0, the Q becomes 0. That is the definition of negative reset. Okay. It's the definition. So reset signal, if the reset signal is 0, then output becomes 0, regardless the input. So if you see that this behavioral model of the D flip-flop, so this is also sensitivity list. So you can find that in the sensitivity list, you can find it's a positive edge of the clock and then negative edge of reset underbar B. So which means that this statement will work, it will be reflected at the rising edge of the clock, the positive edge of the clock, so it's a rising edge, and then negative edge of the reset, because we use the negative reset. Okay, so let's see the behavior. If reset B is negative, so tilde becomes it's not, it means not. So which means that if the reset underbar B is 0, then this is true. So Q becomes the 0. Okay, all zeros. And then if the reset signal is 1, so because it's S, Q is D. Okay. So you can understand. So if you see this code, so you can find that the Q becomes the reset, Q becomes 0 if the reset underbar B is 0 any time. So which means that we don't need to consider the rising edge of the clock or some we don't need to consider any input values. Okay, so the reset signal makes the output of this flip-flop always 0 if the reset interval B is 0. Okay, and then otherwise, in the other case, the Q is sampled by clock signal because you can find the positive edge of the clock. Okay, and so we can define the enable signal here. So enable signal means that it's like here. So this slide shows the right enable signal. So which means that if the right enable is 1, and then at the rising edge of the clock, the Q is reflected by D. So simply at the rising edge of the clock, and Q becomes the D. But if the right enable is 0, even though the clock is the rising edge, clock is at the rising edge, the D is not reflected to the Q. Okay, this is the enable signal. So how can you implement this flip-flop with the enable signal? So we also require the additional input enable. Like so here. Also, this flip-flop has the negative reset. So it's the same. The reset signal is the negative asynchronous reset. So and then otherwise, if enable equal 1, so only the enable is 1, then Q becomes the D at the rising edge of the clock. Okay, this is the enabled flip-flop. Okay, we can write a behavioral model of this flip-flop with the system value like this. Okay, and then so I will show another example. It's a latch. So actually, what this is bug. It's a kind of bug. So we don't actually, except some special cases, you must not generate RISC latch in your design. It's very important. If you generate latch in your design, it's a bug. It's an incorrect design. Okay. So we may need latch for some special cases, but for the normal cases, if the latch is generated, it's a bug. So let's see the example of the latch. So what is the latch? So this is the combinational logic. So we can use the always statement for combinational logic also. Okay. But in the system variable, we need to use the always underbar comb, C-O-M-B, for the combinational logic. So we can use also always statement here. So what's this always statement? So we have the enable signal, but as you can see, this module does not have any clock or reset signal. So this behavioral model means that if enable becomes 1, Q equal D. So what's the matter? So latch means that it's a latch. So latch means if the enable is 1 during the 1, so it's a D, and then if the D is changed during this while the enable equals 1, then Q becomes the same to the D. So that means that D is reflected to Q. But if the enable equals 0 here, and then during a while the enable is 0, even though D is changed like this change of D is not reflected to the Q. That is the definition of latch. But in our digital system design, we don't need latch. We can build the system like a digital system like with the enabled flip-flop, not latch. We cannot use latch. So when you build the combinational logic, like the if as statement, then you need to define all possible selection signal for the output of the combinational logic. So which means that in this statement, we just define the one possible input signal of EN signal. Okay, but you know the EN is it's a big data. So EN can have 0 and 1, 2 cases. But problem is that in this statement, we just define the one condition of EN. And then if we write the code like this, so we just define the one condition of the control wheel, so then latch will be generated. And then this is bug. Okay. So when I worked for some digital system design engineer, so when I learned about the digital system design, my boss or my teacher said that if you generate a latch, then you are a sinner because it's a bug, and then the bug is included in the design. So actually, this is very critical, very seriously critical, because you know the chip is very expensive. Actually, the manufacturing cost for chip is very, very expensive. But if you just add a bug in your chip, then the chip will not work properly. Then each chip is regarded as a stone. Okay, just a stone, not a chip. Okay, so that's why the bug is very critical for the system design. So that's why the hardware design is more difficult than software design. So if we write the software code, and if we generate a bug, a kind of bug, then you can fix the bug by changing your code. But it's not for the hardware design. The hardware design is just fixed, and then actually the hardware design is fixed. If the hardware is fixed, we cannot fix our bug. So that's why the hardware design is more difficult than the software design.
컴비네이션에서는 모든 경우에 대해서 다 결과가 정해져 있어야 되기 때문에 저런 렛치 상황이 버그라는 거예요.
매치가 생성되면 안 돼요. 그러니까는 말을 한 대로 매치는 특별한 케이스만 쓰는 거고 매치 자체가 들어가면 안 돼요. 디지털 디자인. 근데 이제 이런 식으로 이제 그 코드를 짜게 되면은 매치가 생성되게 될 수밖에 없어요. 그게 문제라는 거예요. So he asked about that. Why latch is serious? so as I explained, we just use latch for special cases. Okay, that's why we must avoid generating latch. So when you when you build combinational logics, and then if your combinational logic is controlled by any control signals like this EN signal in this example, then you need to define every possible cases by this control signal. And then if not, you will generate latch. And then usually this is a bug. Then you must, this is the must, okay? You must avoid generating latch in your design. So, because the latch is only used for special cases. Okay, this is the very basic fundamental of the system design. And I hope this is helpful for doing your lab assignment. Okay, let's going back to the process architecture. Okay, so then how can we build a process architecture and the process of hardware? We learned about the instruction sets and the instruction. So just let's see the instruction add x1, x2, x3. So we already, so I believe everyone knows the definition of this instruction. It's very simple. So if we see that this add instruction, we can imagine which operation is required for executing this add instruction. Okay. Okay. So let us assume that this add instruction is in the memory. So I said that the instructions are also data, and then data exists in memory. So let us assume that this add instruction is in the memory. The first, we need to access this instruction with the PC, the program counter. The program counter is the address of instruction. So with the program counter, we access instruction in memory. Okay. So with the PC, then we access the memory, and then we can read this instruction from the memory. Okay. So this is called the instruction sheet. And then, this is the 32-bit data. Right. And then we already learned how to represent instructions with this type of data. It's a 32-bit digital data. So this is just the 1 0 blah blah 1 and 0. Many one there. This data will include many ones and many zeros. Then we need to decode. We need to decode the instruction. What does that mean? From the 32-bit digital data, we read the OP code, read the function 3 field, read the function 7 field, and we can find, this instruction is the add instruction. Also, we can decode the destination register part, and then source register part. Then we can get register numbers for source registers and destination registers. So this process is called the instruction decoding. Okay? Because the instructions has a form of digital data, and we need to recognize which instruction is included in this instruction data. So we need to recognize the register numbers. So okay, this process is called the instruction decoding. So we can know now. We can know this instruction is the x1, x2, x3. And what should we do? So when this add instruction is executed, we first read operands from register file with the source register numbers, right? So source registers numbers are 2 and 3. So with these source register numbers, we access the register file with the source register number 2 and 3, and then receive the data stored in this general purpose register. Okay, this is the register file reading, but this process is also included in the instruction decoding. Okay, and the data is ready for this add operation, so we can execute add operation. So data is ready. Data is read from register file with the source register numbers. And so it's data 0 and data 1. We can get data 0 and data 1. Then we need to perform add operation with the adder. Okay, that's why we learned about the adder hardware. Then result is generated. Okay, this is the just result of the add operation. And this add instruction need to store this result of the add to the destination register. Okay, so this is also the same register file. So with this destination register number and then the result. So this result is returned to the register file. Okay. So I forgot to write. So actually, two data are used for performing add operation. So actually, the add operation is performed. So this process is called execution. Okay, execution, and then the result is returned back to the register file. The result is returned to the register file with the destination register number. So this process is called write back. Okay. So these are required processes for executing the instructions. Okay. And then, so actually, so this example shows the required operation for add instruction. But if we just execute the load instruction, then this load instruction can need to access the memory. Actually, this operation is called the memory operation. Okay. So for the add instruction, we just require the instruction fetch, instruction decoding, execution, and write back. So these operations are required for executing instructions. So which means then we need to build a hardware that supports these operations, like instruction fetch, instruction decoding, execution, write back, also for the load instruction, so memory operation. So you need the hardware need to support these required operations. Okay. Then let's see how can we build the operations. So this is the overview of some very simple CPU design. So in the previous example, I explained about the add instruction as X1, X2, X3, and then I also I explained about the required processes like instruction fetch, instruction decoding, execution, write back, also actually the memory instruction is required. So I explained that during the instruction fetch process, we need to access the memory with the program counter PC. And then in the instruction decoding stage process, we need to access, we first decode the instruction, and then we need to access register file for reading. And then execution, we need to perform some required operations like arithmetic operations or logical operations. So in order to perform these operations, we require arithmetic and logical unit. is called ALU. And then memory. So load instruction like x1, 0, x2, and then for the load instruction, this load instruction need to access memory with the generated address. So actually we need the memory. Also in the write back, in the write back process, we also need to access the register file for write. So these are required operations for instruction. And then in order to support the required operations, we need hardware components. Okay, so as I explained, for instruction fetch, we need the piece, the program count is here. And then, we need to access the memory with the PC, so which means that we require instruction memory. So you may be curious that why instruction memory. So I mentioned that it's a memory. So I just mentioned the memory. So in this figure, you can find that instruction memory. It is because the CPU hardware, the local CPU hardware, the instruction memory part is separate from the data memory part. Okay, it's for performance actually. Actually, the instructions are stored in this instruction memory. But actually, in the real computer hardware, this is the instruction fetch. But I will explain about the cache later in chapter 5. So just remember that in the inside of the computer hardware, instructions are stored in instruction memory, but actually cache, instruction cache. Okay, so we require fish and then we require instruction memory, and then for the instruction decoding process, we require registers, the register file, and then for execution, we require ALU, and then for the memory instruction, we require data memory. And then for write back, we access the register file for write. It's the same register file. So these are required hardware components. And then based on the operation, then you can connect the hardware components. So the previous example, I explained some logics like a module. So hardware, so it's a black box of the hardware, and then it's the same to the CPU design. So these are the module like instruction memory and then register file. So actually these are module, and then as you can see, each module has input and output ports, and then signals are transferred to the other module from the output port of the one module to the input port of the another module. Okay, so we can connect the input and output ports of this hardware component for supporting the required operations like this. Okay, we can just connect. Okay, so I will explain more about this CPU, the baseline CPU design. Okay, in the next class. So I will start here. If you have any questions, do you have any questions? Okay, thank you for your attention, and then see you in the next class.